Now it's your turn. You need to determine the decimal equivalent of the third octet. Calculate the decimal equivalent of the binary number on screen and type it into the table. When you are finished, click Submit. That's correct. The decimal equivalent of this binary number is 28. Click Continue for another conversion exercise. Now you need to determine the decimal equivalent of the fourth and last octet. Calculate the decimal equivalent of the binary number on screen and type it into the table. When you are finished, click Submit. That's correct. The decimal equivalent of this binary number is 11. Click Continue when you are ready to move on. Here is the full binary to dotted decimal conversion of our 32-bit IP address. What is the greatest possible number that can be represented in one binary octet? If we set all 8 bits to 1, the decimal equivalent is 255. So, with 8 bits, you can only represent decimal numbers in the range of 0 to 255. Now that you know how to convert an 8-bit binary number into its decimal equivalent, let's reverse the process and convert a decimal number to an 8-bit binary number. In this example, we will convert the IP address 207.17.137.229. To convert from decimal to binary, starting from the leftmost digit, check whether that power of 2 position fits into your decimal number. In the example on screen, we first ask, does 128 fit into 207? 128 fits into 207 one time, so we set that bit to a 1. We then subtract 128 from 207 and see that we have a remainder of 79. You might be asking yourself, because binary numbers can only be represented with ones and zeros, what happens if the number fits into the place more than one time? Remember that with 8 bits, the decimal number can never be larger than 255, and 128 only fits into 255 one time. Using the remainder of 79, we consider the next lower power of 2. Can 64 fit into 79? Because 64 fits, we set that bit to a 1 also, and then subtract 64 from 79. The new remainder is 15. Moving to the next column, we see that 32 does not fit into 15, so we set that bit to 0, and the remainder is still 15. We also see that 16 doesn't fit into 15. We set that bit to 0 also, and the remainder is still 15. Continuing along, can 8 fit into 15? Yes. So we'll set the 8-bit to a 1 and subtract 8 from 15. The new remainder is 7. By now you can see how the process works. Let's complete the conversion. Can 4 fit into 7? Yes, so we set the 4's place to a 1 and subtract 4 from 7. The remainder is now 3. Can 2 fit into 3? Yes, so we set the 2's place to a 1 and subtract 2 from 3. The remainder is now 1. Can 1 fit into 1? Yes, so we set the ones place to a 1. Subtracting 1 from 1, we have a remainder of 0, and we've successfully converted the decimal number 207 into the binary equivalent shown on screen. To verify our work, we can convert binary back to decimal by adding up the powers of 2 that are turned on. It should add up to 207. Now let's convert the second octet, 17, into a binary number. We quickly determine that 128, 64, and 32 do not fit into 17, so we set each bit to 0. Moving on to the next column, 16 does fit into 17, so we set the bit 16 to a 1. Because we have a remainder of 1, the 8, 4, and 2 bits are set to 0, and the 1 bit is set to 1. To verify our work, we add up the powers of 2 that are turned on and see that it equals 17. Now it's your turn. You need to determine the binary equivalent of the third octet. Start from the left side of the table and enter a 1 or 0 depending on whether the power of 2's place can fit within the decimal number. If it does, subtract that power of 2 and find the remainder. Proceed from left to right as we have demonstrated. Now, you'll determine the binary equivalent of the fourth and last octet. Use the table on screen to calculate the binary equivalent of 229. When you have the answer, click Submit. Here is the full dotted decimal IP address converted into its binary equivalent. We just learned how to convert a binary number into its decimal equivalent and a decimal number into its binary equivalent using IPv4 addresses. Earlier, we mentioned the hexadecimal number system, which MAC and IPv6 addresses both use. Click the Learn More button to learn more about hexadecimal numbers. Now that you know how to convert binary numbers into its decimal equivalent and convert a decimal number into its binary equivalent, let's cover one last topic that also uses the binary number system: hexadecimal numbers. Earlier, we learned that MAC addresses are expressed in hexadecimal format, a numbering system that uses 16 unique symbols to represent the numbers 0 through 15. The hexadecimal numbers 0 through 9 simply represent the numbers 0 through 9, and the hexadecimal letters A through F represent the numbers 10 through 15. The hexadecimal numbering system is just another way of representing binary numbers in an easy-to-read format for humans. The tables on screen show each decimal number, the equivalent hexadecimal symbol, and its binary equivalent. Let's look in more detail at decimal number 5 and its hexadecimal and binary equivalents. The decimal number of 5 and the hexadecimal value of 5 are the same. Each hexadecimal digit or symbol represents 4 bits, which are also known as a nibble. Looking at the 4-bit binary equivalent of 5, notice that we're doing the same power of 2's math as we did when we converted a binary number into a decimal number. This time, however, we're using only 4 bits instead of 8. To represent 5 in binary, the 4's place and the 1's place are turned on. Looking at decimal number 10, you can see that the hexadecimal symbol A and the decimal value of 10 are not the same. In the 4-bit binary equivalent, the 8's place and the 2's place are turned on and add up to 10. Let's return to our MAC address and see how to convert each hexadecimal symbol into its binary equivalent. The first 3 bytes or first 6 symbols are easy to convert because there is a direct mapping from the hexadecimal symbol to the decimal number. In the second byte, 90, hexadecimal symbol 9 is the same as decimal 9. Therefore, the binary equivalent has the 8's place and the 1's place turned on. Hexadecimal symbol 0 is the same as decimal 0, so the second nibble, or group of 4 bits, doesn't have any bits turned on. Starting with the 4th byte, things get a bit trickier. We just learned that the hexadecimal symbol A is equivalent to the decimal value of 10, Therefore, the binary equivalent of hexadecimal A means that the 8's place and the 2's place must be turned on. We also learned that hexadecimal symbol F is equivalent to decimal 15. Therefore, the binary equivalent of F means that the 8's place, 4's place, 2's place, and the 1's place must all be turned on. We have gone ahead and converted the 5th byte. Now it's your turn. Convert the last byte into its decimal and binary equivalents. Type your answers into the boxes on screen. When you are finished, click Submit. That if a device needs to send the same data to every device on the network, it uses a broadcast destination MAC address. The broadcast MAC address is where all 48 bits are set to 1, or an address consisting of all Fs. Now that we understand hex, we can now see how all Fs translates to all 1s. Now that we've covered binary and hexadecimal numbers, let's continue with our discussion of IP addressing. Now that we know how to convert binary numbers to decimal numbers and vice versa, we'll examine how a device determines its network number. But first, why does a device even need to know its network number? Earlier we learned that each broadcast domain is assigned a unique network number, and each device within a broadcast domain is assigned a unique host number. We also learned that devices in the same broadcast domain have the same network number and can communicate directly without the help of a router. Devices in different broadcast domains, however, have different network numbers and need a router to communicate. Until now, we've been using the simple Layer 3 addressing scheme of network number dot host number, so it's easy to tell if a device is in the same network or not. But now we're going to start using IP addresses, so it might not be as easy to tell whether a device is on the same network. Take a look at the example on screen. How does a device, whether PC or router, know if it has the same network number as the device it's trying to communicate with? Each device already knows its own IP address, of course, but remember that information is not sufficient for determining the network number. To determine the network number, also referred to as a network prefix, a device uses its network mask. Here, you'll notice the network mask is 255.255.255.0. Like IP addresses, masks are also 32 bits long and can be represented either in binary format or in dotted decimal format, as shown here. 255.255.255.0 is the decimal equivalent of all of the bits in the first 3 octets being set to 1. The bits that are turned on in the network mask designate the part of the address that is in the network number. Now that we know how binary numbers work, we can see how network masks work in detail. Each bit of the mask has one corresponding bit in the IP address. As we mentioned previously, the network mask has a 1 in every bit position used for the network number and a 0 in every bit used for the host number. When a device needs to determine its network number, it compares each bit in its IP address with each bit in its network mask. If both bits are a 1, the device sets the corresponding network bit to a 1. If either bit is a 0, the device sets the corresponding network bit to a 0. The network portion of the address is exactly the same as the IP address, and the host portion of the network number is always 0. As you can see, the result is the binary equivalent of the device's network number. Like IP addresses and network masks, though, the network number is usually represented in decimal form, as shown on screen. Note that representing the network mask in decimal form can cause confusion because the network mask is not actually an address. The introduction of classless interdomain routing, or CIDR, helped alleviate this confusion somewhat. With CIDR notation, also known as slash notation, the address is still shown using dotted decimal format, but it is followed by a / and the number of bits used in the network prefix. The number after the slash is also known as the prefix length. In the example shown on screen, the bits in the first 3 octets are all turned on, meaning that the first 24 bits are network prefix bits. So 192.168.1.8/24 means that the first 24 bits are the network prefix, and the last 8 bits are host bits. We can also use CIDR notation to identify a range of addresses. So 192.168.1.0/24 identifies the address range starting at 192.168.1.0 through 192.168.1.255. Now, you might be thinking this all seems pretty obvious, and in this case, you are right. The first 3 octets of the IP address, represented in decimal fashion, are 192.168.1. And because the prefix length is 24, the first 3 octets of the network number must also be 192.168.1. When the network mask falls on an octet boundary, such as a prefix length of 8, 16, or 24 bits, determining the network number is fairly straightforward. But it is a little harder to determine the network number when the network doesn't fall on an octet boundary. Originally, IP network numbers always fell on an octet boundary. With the advent of CIDR, network prefixes could be any length and often don't fall on an octet boundary. The older system of routing was called classful routing. CIDR, if you remember, stands for classless interdomain routing.